Check, check. Presentation. Okay. Use the arrow keys, but you will only see it change on these screens. First, there's a glitch that doesn't allow it to change here. Okay. So up and down arrow keys here, and just watch it on the. Don't get distracted by the fact that that's not there. Other than that, you are all set and you're live.
Hi everyone. The session continues now with Suri Das from Oracle, and Suri will present supporting neighborhood-aware path traversals with graph queries. So Suri, up to you.
Hi. So this is a very different content than the other presentations probably that you have heard here so far. This is more at the basic level, right? And I'm trying to see what's the state of the art in graph query languages, and a little bit on the modeling side also. And then I'm trying to say that there is basically I'm suggesting some approach, to plug that hole that we have there. So, okay, this is how I looked 5 years ago. So slightly older.
We're activating the camera. I think we see you now. Yep.
Yeah, it was working.
Okay.
Hold on 1 second. Sorry about that.
So this is the overall outline, background, and motivation. Then going some approach that I would think would be useful, and then some constructs on that, and then summary and future work. So firstly, I called it neighborhood-aware path traversal, right? So let me explain the terms a little bit before we get into the content. So this is the terminology I am using. It's not necessarily universal, right? So you have a path. That means you're going from a start to a finish, right? And in between, you have all these edges that have matched the path criteria, right? So we have a sequence of edges going from start to finish. And so in the edge, we have two kinds of, the edge, if you look at one edge, it's two vertices connected by a link, right? And we call it head vertex, and I'm calling it head vertex, and tail vertex. This is not necessarily the edge direction, right? It's how the edge was mapped into that path. It could be reverse, forward, or it could be undirected also. So edge in the case of property graph is essentially head, link, and tail. And the link could have a direction, like forward, reverse, or undirected. And link has one or more labels. And link has some edge properties essentially there. In the case of RDF, if a triple has matched that particular edge shown there, right, head, link, and tail, then depending upon the direction in which it matched, right, the triple is either head, predicate, tail, or tail, predicate, head. So just so that the direction of the path and the direction of the edge or the triple in the case of RDF, right, is not necessarily same. They could be opposite. So again, this is just terminology. And so that's an edge. What's the neighborhood of an edge, right? I'm talking about neighborhood-aware path traversal. So you should understand what a neighborhood is, at least in this talk. So neighborhood can be vertical or lateral or inline and horizontal, right? So this is a vertical. That means it's kind of, if you consider the path to be going horizontal, right? Vertical means I'm looking at all the edge properties, all the properties of the vertex, right? And in the case of RDF, in the case of vertex, it could also be links, also other edges going out from there. So vertical neighborhood is the to or from the endpoint vertices and to and from the link, right? Kind of going away from the line. And then this is the inline or horizontal neighborhood. That means it's basically along the path. So you are a current edge. You are looking at the current edge. You are processing the current edge, right? Your previous edge on the path is a neighbor, right? And so on, previous to previous edge is also a neighbor, right? And similarly, next also, in case we have that information. So that's the inline or horizontal edge, horizontal neighborhood, I mean. And so a neighborhood-aware path traversal, right, is something that may need to access the lateral neighborhood going away from the path, or lateral neighborhoods of the edge, of the neighborhood edges that you have, inline neighborhood, right? You're at a current edge, your lateral neighborhood of the previous edge is actually also maybe needed for figuring out whether you want to keep the current edge or not, right? So just to give, okay, let's see. Before I go into this one, actual example, just a quick thing, right? Think of this, you are doing a tunneling, right? You are digging this tunnel one segment at a time, let's say 100 meters at a time, right? And you saw a little bit of water in there, a little bit of water in the current edge, right? As such, it may not mean much, but what if it's actually double the amount that you saw in the previous, double the depth that you saw in the previous segment? There is some concern there. Is it increasing? So you need to know the trend, right? You cannot just say, I'm just going to look at the current edge and that's it. I don't need to know anything else. You need to understand how things are as you have traversed, right? So that's kind of the thing that I'm talking about, kind of gives you the motivation. In practice, it's extremely important. In any engineering, right? You have to know what's going on, what's the trend, before you can say that, yeah, this looks good or not, doesn't look. Okay, so motivation, this whole bunch of slides, 11 slides. I'll give you a couple of examples and show the current status of what we have right now, right? So this is a simple one. Here, and this is very abstract example. You can map these abstract examples to any kind of practical. There are lots of practical situations into which it maps. So this is the colored vertex graph. That means only in this graph, only the vertices, each vertex, right, it has a color. The edges are not colored. So colored vertex graph, it's A and D are red, B and C happen to be blue and green, and there's a nose is a relationship between them, right? And you can have that represented in your relational table. It's a person table, and then there's a nose table, which is a relationship table, right? So entity and relationship, and the nose table has two foreign keys, who and whom, both go to the person's name, and you have it that way. In RDF, you have it as triples. A has name A and color red, and so on. And finally, the actual edges or linked triples, and that actually have the object property. Those A knows B, B knows C, and B knows D, C knows D. And property graph I'm not showing because this is very easy in property graph, right? Extremely easy to show, and there are different syntaxes. So I'll leave that one out. And this is a more problematic data set. This is where this is called a colored edge graph. That means vertices are all do not have any color, but the edges actually have color. You can think of this as a type of relationship, right? A knows B intimately, or B knows C casually, and so on. It could be the color could determine many things. In relational terms, I reduce the complexity by taking out the person table. It simply says who, whom, and color. A knows B, red, B knows C, blue, B knows D, blue, and C knows D, green, right? What do you do with RDF? Shifted lights, okay. So in RDF, actually, it's not supported today, right? So we have to look at extension. RDF does not allow, classical RDF, right, does not allow edge property. So RDF star has been proposed. In RDF star, this can be represented like that, where A knows B, and then inside that curly brace and so on, right, you say color red. That means the A knows B, that edge or that triple actually has the property whose color is red, property that color is red. Similarly, B knows C color is blue, and so on. So I showed that as an example here. C knows D, and that C knows D represents essentially this triple, right? Okay, so let's look at this query here. Select X, Y color, and this is in SPARQL star, right? X knows Y, and I also want to know the color of that one. It's a simple query. All I'm asking is give me the edge property, give me the color of the edge, right? And the result is, again, very simple. AB, red, essentially the copy of that. AB is red, BC, blue, and so on, okay? the problem is that happens is this. Suppose I add a multi-edge. Now, multi-edge is a terminology that I have used before. I believe some people use that. Other people have called it multiple edge instance, or has called it multiple edge instance, right? But basically, that means I have multiple edges going between. Think of this: Brazil wins soccer World Cup, right? There are infinite number of times they probably have won it. So each of them is an edge, is a distinct edge. One is in 1994, one is in 2002, so on, right? Roger Federer wins Wimbledon, how many ever times. So here, let's take that as an abstract example. Suppose I want to add this. You see C knows D. There's a blue edge now, right? C also knows D in some other way, let's say. So how do you represent that in RDF star? Firstly, in relational terms, it's like this. You have to actually create an ID for each row, because CD is not, it becomes a duplicate now, 2 CDs there. So I have to create an ID that becomes the primary key, and then I can say, yeah, row number 4 CD is green, row number 5 CD is blue. Look at the situation. We actually had to introduce an ID there. Without the ID, I won't be able to represent that, right? So in the case of RDF star, though, we have a problem with that, because RDF star has implicit identification that is based functionally on the SPO of the triple. Therefore, it cannot actually handle that. So I looked at even the latest copy of the RDF star community group, W3C community group specification, and that says basically use an occurrence of the triple. So let's say we do that. So if you look at the bottom here, I don't know how to show my mouse here, but let's arrow here. Essentially, I added this. C knows D has an occurrence, CD2. So I created an extra occurrence there. And underneath that, once I get that ID, CD2, right, as an occurrence of the triple, then I can say CD2 color is blue. Okay, so the original one remains, and I create a new occurrence of that triple whose color, then I can say, after that I can say that, oh, that occurrence's color is blue. The problem that happens, which many people don't recognize, is this. The extra hop that I created, right? Whether I created that only for that, but one extra, or we replace the original one with 2 occurrences, the original query that was sitting there that some people may have written and left the company, okay, will now give a different answer. Which one is missing? CD blue is missing. What that means is that now the company has to say, oh, my model changed because of this new data that came in, right? And now I have to rewrite my old queries so that they work again, give me the correct result, right? So that's a big problem in terms of cost in an enterprise setting. They are not going to have a little query like this and one query like that. They will have thousands of queries which are dependent on what properties you have in your data set, right? And suddenly they will say, oh my God, I have to write this 1,000 extra queries now, rewrite those queries. So that's the problem with RDF stars, that thing about implicit ID generation based on SPO. So what is the solution to that? So this is a second data set still, right? I called it RDF2M because it's like multi-edge. So let's look at the solution to that, essentially. So we have, I have proposed a new RDF model called RDF-N. N stands for name, essentially. That means the idea is that every triple there in the RDF, right, must be named. And this is very similar to property graph, actually. Property graph has this idea, okay? Dan likes Anne 3 times, right? You can just draw 3 edges, and there's no problem. Each of them has a distinct appearance. Each of them can have a different color, liked in 1989, liked in 1999, liked in 2009, fine. Okay, so here, in the syntax is very simple. A knows B, and this is the ID, _:AB. And then I can say anything about that by saying _:AB, color red. Now, this _:AB actually is not a blank node. It's just an alias that refers to whatever name the system generated, because the system automatically generates the name. Remember one thing, if I ask everybody to name their triple, it's going to be a big burden on them, right? So we want things to be automatically generated, except in the case of multi-edge. When multi-edge happens, we cannot do that. So the original query, right, I could write it like this: X knows Y, E color is that color, right? And it returns 4. Now I add this extra triple, which is very simple, C knows D, and I put a different ID. This is the URI. This is not automatically generated. This is the user has to give this, assign this URI. So let's say CD2 color blue. So representation-wise, everything looks good, right? I can represent it. There's no problem with that because every statement has an ID, irrespective of what their SPO content, the subject predicate object is. So now look at that query there. The same exact query, right, will now give this result, CD blue there. So your query remains unchanged, even though you have suddenly, some country which is not supposed to win World Cup twice, actually won it twice unexpectedly, right? So, so that's essentially the data that we are going to use as a second data set. Okay. So now the last step is here. Now, if you notice this, this can be easily we can create a shortcut for that. And just to align with RDF star, I just made it same exact as RDF star. Because there's nothing special about it. Underscore colon AB, and then underscore colon AB has some properties. I could merge that into that because in this case, the name of this is automatically generated. These are all automatically generated. The last one, though, is user assigned. Okay? Similarly, the query can also have the original SPARQL star syntax. It's just a shortcut. So it's very close to RDF star. However, it has that capability to handle multiple edges or multi-edge without damaging your pre-existing queries. Okay, so this is the data set that we're going to use. Okay, now let's see the motivation next. So here, firstly, only minimal support. Property graph query language supports only 2 out of 5. I'll give 5 examples, and SPARQL supports only 1 out of 5. Query 1. Okay, this is a vertex graph. It's a simpler case. Is the vertex D reachable or not? Right. Query 2, V and E has 2 versions. One for the vertex colored graph, and one is for the edge colored graph. No 2 adjacent colored elements have the same color. See, this is where color neighborhood becomes important. Is my previous one also the same color or not? Right. And the third one is a little complicated, more just extension of that. No 3 adjacent colored elements share any color. So in general, I don't have to stop at 3. I could say n, right? So just to give an example of that, it can be extended. So let's look at this one. This one, reachability. We all know that it works. PGQL, it works. X knows plus Y. SPARQL also it works. You can use property path, knows plus Y, right? That transitivity. Okay. Now comes the next query, which is the 2V case, which is in this case, reachability plus a constraint on vertices on the same edge, right? So this is actually works in PGQL. So because in property graph query languages, you can actually designate this U and V, and then where U dot color is not equal to V dot color, and then say, okay, I want such edges. I keep on going on those edges, right? That works. SPARQL doesn't have that. SPARQL does not give you any visibility to the internal nodes. So going to the next one, this is the one that is 3V. That means here, the vertex colored edge, no 3 adjacent vertices must not share. They should not share any color. Okay, so this again is it's not supported in PGQL because PGQL or property graph query languages support only one edge. It does not allow you to see the previous edge or next, 2 edges from the current edge. SPARQL, of course, does not support it. It has even lower visibility. Now coming to the edge graph, edge colored graph, right? First is a very simple. Is D reachable from A where no 2 adjacent edges have the same color? That means I have to know about 2 edges, right? Only then I can compare. Neither property graph query language nor SPARQL have that ability to look at the previous edge as we are traversing in a query, right? As we are traversing. This is the thing I was talking about when I said that whether the previous segment in your tunnel segment, as you're doing the tunnel, had how much water it had. Can I compare that with that one? So similarly, 3E is just an extension of that, 3 adjacent edges. Obviously, if it does not do 2, it doesn't do 3. So that's why I said 1 out of 5 and 2 out of 5. So what is the summary of that? The main problem. No access to any interior elements along a path in the case of RDF. In the case of property graph, no access to same thing except the elements of the current edge, right? So you can look at the lateral things there. So next, let's see. So what is a solution to that, right? Some ideas on that. So the first thing we need is a notation, right? So this is the current edge, head, current, and tail. And edge connects a head vertex to a tail vertex, and direction, as we said earlier, forward and reverse and so on. So we can call it edge 0. The previous edge, we can call it edge -1. The next edge, we can call it edge +1, and so on. So it's like almost like a subscript saying how relative to the current edge, how far are you do you want to see, right? And that actually leads us to this notation. Here, again, this notation is completely, I just thought about something. You can always actually change it from, instead of E, you can call it edge if you want. So EI, when I is equal to 0, it's the current edge. I equal to -1 is the previous edge. I equal to 1 equal to next edge. I equal to 2 will be the next to next. I equal to -2 will be 2 from now, and so on. So in general, it is a system may not allow all of them. It's I can do at most 5 or at most 3, which is fine. And then other things like direction and ordinal number. That means which is the position of this segment in the path so far, right? And this one we don't have to. It's there. It's like multi-segment edge, right? What is a variable length path? It's like one segment, which each segment could have 2. How many repetitions of that, right? That's essentially a multi-segment variable length path, right? And we could use a second dimension, J, to indicate that the edge number in this segment, inside a segment, what is the edge number we are talking about, right? So, but we'll not take up this anymore. So after this. So here's a solution that idea that I'm saying. Again, this is nothing sacrosanct about it, right? This is just an idea that I think people, hopefully some people will look at it and say, yeah, we need to do something about it. Notation syntax can be different. So here we introduce this path and match. In the case of SPARQL, remember SPARQL did not allow this, support this. Property graph actually supports that. So in the case of SPARQL, we say, okay, nose class, and then path, that's just keyword, and match. And inside the match, you actually have a pattern there. And that pattern is saying H0, that means my current edge is head, and current edge is tail is T0, right? Color of the head, color of the tail, they must not be equal. Only then the path and that edge will be included. Otherwise, it will not. Okay, and so that will allow SPARQL to. I guess things are a little bit misaligned here. I don't know why, but Apple, Mac, and this one may be different. So that's basically what I explained. Now, how about separate edge vertices? Remember, property graph query language even that does not support that. Right? So to support that, in the property graph case, we can use the same notation. Again, the notation is the main thing here. The notation actually is saying where R0 is, let me put it here, where U dot color is not equal to V dot color. That means I definitely do not want the colors of the current edge to be the same. And if it is not the first edge, then I also need to know that my V dot color, my tail, should not be the same as the head of the previous edge. That's how I get all 3 of them, right? So again, just using that notation, we can actually support that. And same thing with SPARQL. So this is just showing, the steps, which is pretty easy to understand. But in SPARQL, the same thing on separate vertices, right? Similar notation. H0, T0, we already saw. That means they are the current edges, head and tail, right? And then that optional actually captures the previous edge's color if it is relevant. If it is first edge, it's not there. And if it is not first edge, in that case, the pink one here, in that case, it will check for the color of the current tail and the current of the previous head, CHP, color of the head previous, right? They're not the same. So you can look at the details for this a little more if you want, but thing is later on. But that's basically the idea, okay? And again, we go there, colors of the A and D are the same. This thing does not satisfy. This thing doesn't, that path will not be picked. Whereas this path is okay because any three consecutive edges, they have different, they have the 3 different colors for the vertices. And then 2E, let's just to take this example, I'll probably skip the after this, is that is D-reachable from A, where here we need two edges, right? The edge, I want the edges to have, consecutive edges to have different colors, right? So it's, I'm showing it here for a property graph case, and it's simply saying E-1 and E0. Okay, that's all we need. E0 is my current edge, E-1 is my previous edge. I just want to see their colors are not the same. Okay, this I don't need to do. And in the case of SPARQL, similar. The idea is that E-1 and E0 has color C, right? And then E-1, if it is not the first edge, pick that color CP, and then make sure CP is not equal to C. If it is first edge, I don't really care. So I don't have time for that one. So similarly, 3E will be a little more complicated, right? Where we want to see the colors of the three edges that I have in my disposal, right? I want to make sure they have different colors. So you can look at that in more detail later on. I think, I'm not sure how I'm doing it this time. So basically the thing is that, and in SPARQL, it's again similar. All we are doing is E0, E-1, and E-2. I'm referring to those three to get the appropriate information and putting that in the match clause there. And that's all I need to make sure I'm okay with respect to the path neighborhood constraints. Okay, I'll not go into detail. These are all there in the PDF. Only. Okay, so let me, I'll show just the one thing about the retrieval. There are additional things, top K and having filter. In the retrieval case, we want to retrieve the information also. So all we do, here I'm showing only SPARQL because property graph has things already. I don't want to get in that. In SPARQL, besides the match, you can put a project. Anything that's coming out of this graph pattern in the match clause, you can actually pick that up and project it, and then that can be selected, get selected from there. Okay, so that's how we can project the path, actually, right? All the list of vertices and so on. So that's something very important to do in SPARQL because we don't have anything like that today. So let's see. Okay, I don't have to. Let me go to the last slide because it's only 2 minutes. 1 minute, okay. Going down quickly. So here's a summary. So main takeaway is this, right? Again, I mean, this has nothing to do with any product. This is RDF. This is property graph. We are talking about SPARQL. We are talking about property graph query languages, right? So the main takeaways are, what is the motivation for this? Network-aware path traversal is very important. We don't want blind tunneling, right? We want to, as we are doing a path traversal, we are supporting path traversal, right? We want to make sure you know what's going on, trends, right? You can say it has to be beyond more than the moving average, all those things, right? And current support is actually minimal. Proposed approach, main thing is the notations, the ability to reference your current edge and the previous edge and ... right? As much as your system wants to allow. And there could be some system imposed limitations. And then looking ahead, this is what my goal is, right, to this, is that, remember, when somebody comes up with a standard, we are the people who actually go and implement that. If the standard is not good, then our work actually goes in vain, kind of, right? It doesn't work. People don't adopt it. It's like, why did I spend that much time, debugging time and so on? So I hope that language experts from both property graph and RDF communities would recognize the importance of this and build on essentially the ideas from here. The good news, to end, is that prominent members of SQL PGQ standards group that I have talked to, they have actually expressed their agreement regarding the importance of NAPT, and they want to take it up in a new version. Okay, so that's on time.
Thank you very much, Suri. Unfortunately, we don't have time for questions, but again, Suri is on Slack, and here at the conference, so feel free to ask him there. Thank you.